In this video, we're going to talk about a second way to do amortized analysis, what we call the banker's method. The idea here is that we're going to charge extra for each cheap operation. So it's sort of like we're taking the example where we looked at saving money for a car. We're going to actually take that $100 and put it in the bank. And then we save those charges somewhere. In the case of the banker, we put it in the bank. In our case, we're going to conceptually save it in our data structure. Okay? We're not actually changing our code. This is strictly an analysis, but we're conceptually thinking about putting our saved extra costs as sort of tokens in our data structure that later on we'll be able to use to pay for the expensive operations. Does it make more sense as we see an example? So it's kind of like an amortizing loan, or this case I talked about where we're saving $100 a month towards a $6,000 car because we know our current car is gonna run out. Let's look at this same example where we have a dynamic array and we have n calls to pushback starting with an empty array. Okay? The idea is we're going to charge 3 for every insertion. So every pushback, we're going to charge 3. 1 is the raw cost for actually moving in this new item into the array, and the other 2 are going to be saved. So if we need to do a resize, in order to pay for moving the elements, we're going to use tokens we've already saved in order to pay for the moving. And then we're going to place 1 token, once we've actually added our item, 1 token on the item we added, and then 1 token on an item prior to this in the array. Okay? It'll be easier when we look at a particular example. So let's look at an example. We have an empty array. Okay, and we're going to start with size 0, capacity 0. We push back A. What happens? Well, we have to allocate our array of size 1 and point to it, and then we put A into the array. And now we're going to put a little token on A. And this token is what we're going to use to pay later on to moving A. In this particular example, for the very first element, there's no other element to put a token on. So we're just kind of waste that third token. We push in B. Okay. There's no space for B, so we've got to allocate a larger array and then move A. How are we going to pay for that moving A? Well, with the token that's already on A. So we prepaid this moving A. Okay? When we actually initially put A into the array, we put a token on it that would pay for moving it into a new array. So that's how we pay for moving A. And then we update the array, delete the old one, and now we actually put B in. So we put B in, that's a cost of 1. We still have 2 more tokens to pay. So we're going to put 1 on B, and we're going to put 1 capacity over 2, that is 1 element earlier. So we're going to put 1 on B. So we've spent 3 now, 1 for real, and 2 as deferred payment that we're going to use later in the form of these tokens. Remember, these tokens are not actually stored in the data structure. There's nothing actually in the array. This is just something we're using for mental accounting in order to do our analysis. When you push in C, we're going to allocate a new array. We copy over A, and we pay for that with our prepaid token. We copy over B, paying for that with our prepaid token. And now we push in C. That's 1. The second payment we have to make is we put a token on C, and then we put a token on A. 4 divided by 2, that is the capacity divided by 2, are 2 elements prior. We push in D, we don't have to do any resizing, finally. Okay, so we just put in D, and that's cost of 1. Second, put a token on D. Third, put a token capacity over 2, or 2 elements prior to that. So notice, what we've got now is a full array, and everything has tokens on it, which means when we need to resize, we have prepaid for all of that movement. So we push in E, allocate a new array, and now we use those prepaid tokens to pay for moving A, B, C, and D. Get rid of the old array, and now push in E. And again, put a token on E, and a token on A. So what we've got here then is order 1 amortized cost for each pushback. In particular, we have a cost of 3, right? So we've clearly seen. So let's look back at how we did this. For this dynamic array, we decided we had to charge 3. And other data structures with other operations, we may have to charge a different amount, right? We have to figure out what will be sufficient. In our case, 3 was sufficient, and we decided that we would go ahead and store these tokens on the elements that needed to be moved. So it's a very physical way to keep track of the saved work that we have done, or the prepaid work that we have done. So we charge 3. 1 is the raw cost for the insertion. If we need to resize, we've arranged things such that whenever the array gets full, we've actually, in order for the array to have been full, we had to have done enough pushbacks such that every element got a token on it. All the new ones that we added since the previous resize, plus every time we added one of those new ones, we prepaid for a prior element as well. So we pay our 1 insertion, we pay 1 for the element we're adding now, and we pay 1 for sort of a buddy element earlier. The next video, we're going to look at a third way of doing amortized analysis, which is the physicist method.